You can already see it. 792, the factorial stuff. Number 18, woohoo! Look at that, Pascal's. Not as good as mine, but, ooh, I should check mine. Did I get that right? Oh, we checked it yesterday. I got that one right. 45. True. But, did you have to do Pascal's to get there? Nope. 10C2 is 45 as well. Number 24, the full expansion. Check it. Did you guys get your negatives, positives okay? Think of it as y plus a negative 2. So when you plug in a negative 2, that'll be a minus in the term. Negative 2 squared becomes a positive. Negative 2 cubed is a negative, etc., etc. Number 32. Whew. Check that puppy. Can you guys even see it? It's kind of small. You have another negative plus negative 5y. Yeah, Cream. Not necessarily, because theoretically Pascal's isn't that hard to get for the fifth row. So you could have done Pascal's and it was 1, 5, 10, 10, 5, 1. Yeah. But this is just a reminder of how we can jump there if we need to. Does that make sense? We can either jump to a row if we need to, because, like, for instance, guys, if I was to ask you for the binomial coefficients of the 10th row in Pascal's triangle, what's one way you could get me all of them? Do Pascal's. What's the other way? How would you start, though? How would you do that expansion? What would the first coefficient be? 1. It would be 1, but how would you find it with combinations? N is your 10, and then what do we put as R for the very first term? 0, because the second term isn't there. So it'd be 10C0. What would the next term be? 10C1. Next term? 10C2, 10C3, 10C4. We can get all of them just with combinations, too. Luke?
How do you use those combinations to find coefficients?
Well, if you're trying to do the entire expansion, like with Pascal's, you could have done Pascal's all the way down to the 1, 5 row. Or you could have started at n is always for whatever power you're raising it to. N is the first number. See how it's all 5, 5, 5, 5. And then we start for the first term. Remember, R is the power of the second, but the second's never there in the first term, so we start at 0.
I'm just wondering how you use 5 and 0 to get the first coefficient.
Like you solve the combination. And the combination would be 5 factorial over n factorial over n minus r. Long story short, you get 1, and 1 is the first number. Does that make sense? So we solve something. And do you guys realize if you were solving, don't you only have to go so far? Like once you have 1, 5, 10, 10, don't you know that it's just going to be 5 and 1? There's that symmetry in Pascal's triangle. Sure. Okay, so number 50, you guys can already check how they plugged it in, how they jumped there. 32,480 to the 4th. Number 54 and 88. I think that's the end, right? Let me give you a second. You guys able to jump this? Did the example from yesterday help? A little bit. I think they said x to the 8th. Wasn't it? Oh, x to the 8th. So didn't you have to put in your x squared and say what power to get it to the 8th? Plug in at 4. 12 was the total, that's 8, so then 8. Are these easy problems? No. Is it easier than going to the 12th row of Pascal's triangle? 13th row, technically. Yeah. The book is continually doing this whole NCR just because it's more obvious what it is. But if you guys are using the parentheses, well, I don't think the same. Okay, we're good? Any questions on odds? Which one? 50? Is that what you said, Ella? Okay. That's okay. 50, you had a question on anything else? I heard someone say something, but I have no idea what it was. Okay, just 50. Let me get rid of that. Let's get back to this. Let me get out of normal pre-cal. This is one reason why we have to keep going, because they are catching up. Nice thing is we're doing a huge chapter 9 test on, not huge, but a whole chapter 9 test. Pre-cal's doing like 9-1 to 9-5. Take a test and then they're doing like a separate quiz on probability. Just helps them to break it up. Okay, Ella, do you have the question for number 56?
It's 5A plus 6B to the fifth.
Oh.
And then it's asking to find the fifth.
How did you guys think about this one? When it says find the fifth term.
I just looked at the example they had, times like took the bones and then applied it to that.
What's going on in the fifth term? If you were to think about the terms, now there's a lot more than that, right? And technically this is a polynomial, so shouldn't there be like pluses in between? It's not a sequence per se. Let's just think about one little baby part. What's 5a going to be raised to in the first term? Just one baby part. We're not thinking about the coefficient, even though we should know that's 1. We're not thinking about the 6b, whatever is there. What's just the 5a doing? Raising to the fifth power. Why? Because it starts at the top, right? Top down. What's 5a doing in the second term? How about the third term? How about in the fourth term? Sorry, 1, 2, 3, 4. There we go. How about in the fifth term? We don't have to know everything to be able to zoom in and say, hey, we know something. We need, remember from yesterday? We know 5a will be raised to the first power. 6b, well, hold on, let's fill in a few things. Remember from yesterday? We could fill in those are the things we need to fill in. What's something we can fill in? If this is 1, and both the powers have to add up to be, what was our total degree? Then this must be, the power of 6b must be 4. Because that's 4, what else is 4? The bottom of the combination. Careful, what should go on top? Another way of writing that, the book would have written it as 5c4. Aren't these the exact same thing? So Ella, to be honest, that's how I would have done it. And then you can plug and chug in the sense of your NCR formula, and then 5a times, let's see, where did we go? We do our little 5 times 4 is 1 factorial, 4 factorial, times 5a times 6 to the 4th, b to the 4th, and then dot, dot, dot.
So when it asks you to find the nth term, you just have to find it.
Basically, you count it, or if you want to think about the fifth term would be, I always use the first term because it's the easiest one in my head, because the first term starts at the highest or at n. So the first term, n is 5, or I should say the power of the first term is 5, and then 4, and then 3, and then 2, and then 1. You could think every polynomial is going to have one higher term. So the fifth degree is going to have 6 terms.
Oh.
So then you can say the fifth term is 1 away from the n term, which is always the constant. There are a few different ways of getting there, but somehow I would think about, if I'm in the fifth term, figure out either the power of, let me get my little highlighter out. Think about either what this guy has come down to, or think about what this guy has become from the other side. That's probably the easiest.
But when it tells you just to find the coefficient,
Then you're just stealing 5c4. Does that make sense? So from this, sorry guys, I didn't think about the division. They're just asking for the coefficient, so they're just literally asking for, wait a minute, but you can't forget the 5 and the 6 to the 4th, right? So we would put all of that together. then you would have a times b to the 4th left. All right, cool kids. That was a very tricky one. Hopefully our examples from yesterday helped, and hopefully the extra time helped as well, but we got to keep on going.
So we put it in.
For sake of time, this is a great probability intro, but let's go ahead and just get going, yeah? We started taking notes yesterday anyway, true? Or you were supposed to, last night. Section 9.6, counting principles. Let me go ahead and help you guys separate 9.6 and 9.7 real fast in your minds before we start. 9.6 talks through strategies of counting up the possible ways something can occur. 9.7 says, okay, let me put a special condition on it, and I want you to give me the chances that it actually will occur. 9.6 is how many different ways, or as the wording says, the number of favorable outcomes of a situation. 9.6 says how many different ways could that happen. 9.7 says what are the chances. So for instance, without knowing any of the weather reports or looking outside today, how many different ways could it have rained this week? This school week, we'll just say Monday through Friday. How many different ways could it have rained? Kind of. A lot more than 5 though.
We got 1, 1, 1, 1. And we got 1, 1, 1 and 2. And 1, 0, 2. We could that way. Then switch it and that way, over last one. And then 3s and then 4s.
But how? How do you do it? We have 5 days, Monday through Friday.
The NPR.
NPR? Maybe. That's not going to do quite as many as though. Meaning, could it have rained yesterday? Could have. I mean, we're not going to talk about the chances on like the weather report. Could have rained yesterday and not rained the rest of the week. True. But it could have rained, this is what Sean was trying to explain. Couldn't it have rained today and not yesterday and not the rest of the week? Yeah. Could it have rained yesterday and today and not the rest of the week? Yeah. Could it have rained tomorrow but not today, but it did rain yesterday and then Thursday and Friday also. Do you guys see how, oh my goodness, there are a lot of different ways it could rain this week? Does that make sense? It could have not rained any of the days. It could rain every single day, or it could rain 1 or 2 or 3 or 4 or 5 different days, but in lots of different orders. This is the idea of how do we count up all of those options? Are there strategies? And sometimes, usually the answer is yes. There are strategies, and we'll talk about some of them. But that is not what probability is, and that's section 9.7. 9.6 is how many different ways could it happen. Section 9.7 is, okay, what are the chances? What are the chances? Now we're not going to go into the weather reports and all that sort of stuff. Let's instead use the idea of flipping a coin. Let's assume that we don't have a weighted coin. There's a lot of kids that do that. Universal Studios. Are you going to? Take Richmond's back. Okay, coming back. The chances, how many different ways can a coin land? Assuming it lands normally. 2, heads or tails. Some of you are like, they can land in the middle. Okay, that's right. For sure, I guess you'd say that. We'll just say heads or tails. How many different ways could it land? 2, that's section 9.6. What are the chances you get heads? 50%. 1 out of 2, 1/2, right? That's probability. Do you guys see the difference? That's 9.7. So 9.6, we're dealing with how many ways, counting up the possibilities. 9.7 says, okay, take the total number of possibilities, take the total number of ways that this certain special characteristic can happen, and make a fraction out of it, a percentage, a decimal. Okay? So 9.6, we're just going to get really big numbers. So let's think about real quick. Old-fashioned way of finding the number of favorable outcomes in a situation or of a situation. Identify them all. And count them up. Wait, hold on. Seriously? Isn't that the old-fashioned way? Yeah. How do you find the number of favorable outcomes? Identify them all and count them up. And that's what you guys just did with the whole coin flipping example. I said, how many ways can it land? And you said, oh, hey, I know a coin has two sides, heads and tails. Sweet, two. You identified the different sides, and then you went ahead and counted them up. But then the next part says, but sometimes there are too many to count, so we need some sort of strategy. We need some sort of strategy. So we're going to cover in section 9.6, counting principles, a few formulas, a few other clues. And one of the questions we ask is repetition allowed or not? Another one that we might ask, and this is the one that Luca was saying, or is order important? Okay, this is giving you just a grand old introduction to section 9.6. Let's start solving for stuff. Sound good? Determine the number of ways a computer can randomly generate one or more such integers from 1 through 12. Such that an integer is divisible by the 4. Now, the highlighting, the number of ways. Is this a fraction or a percentage? And the answer is no. The answer is no. We haven't covered any formulas. We haven't covered any fundamental counting principles. So I'm assuming this is something that we can think about and count up. So what's our restriction, or what is our scenario? What's the computer choosing from? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many different ways can it randomly generate an integer divisible by 4?
3. Almost 3 of the numbers. There's 4, 8, 12. There's 3 like 4. But then we have to think about how those will be arranged within the random sequence.
There's just a number of ways. It's 3. Is it 4? 8 and 12.
We're thinking about all the different numbers it could choose from. It can choose any of the numbers 1 through 12, and how many does it have to choose from? And the answer is 3.
Because order didn't matter.
Now the reason, Sean, that you're getting stuck up is you're thinking one or more such integers. The reason why is because this one category of directions was given for 11 and 12, or sorry, 11 and 13. For 11, how many is it choosing? Just one. For 13, how many, do you see what I mean? So they went ahead and said, hey, use this for both of these problems. Number 11 is asking for just one number, so 4 or 8 or 12. There are 3 options. Number 13, here's where it gets a little bit interesting because now it's doing 2 distinct integers. Does that make sense? Good thinking, though. You're ready for what comes next. Okay. How many ways can it come up with 2 different numbers that add up to be 9? 1 and 8, 2 and 7, 3 and 6.
Then do you consider the flit side of it?
What's it saying? How many ways can it randomly generate 2 distinct integers whose sum is 9? What are they asking when they say, can it be flipped? Because right now we've counted how many different options? 4, right? But the question is, would 8, 1 be a different set of integers? Would it be a different set of integers? No. Would it be a different order? Yes. Or would it be a different set? And the answer is no. So we're still going to say how many possible outcomes are there? 4. We're thinking about the possibilities. Either 1 and 8, 2 and 7, 3 and 6, 5 and 4. There's nothing to point our attention to. 8 and 1 being a different, or needing to be counted differently than 1 and 8. Now, these are all questions, though, that we are going to have to answer as we move on. What was going on in that example? We can think in our head of all the different numbers 1 through 12. We can think about how to put them together in order to meet a certain condition. But as soon as the numbers start getting bigger, as soon as the number of possible outcomes start getting more complicated, here's one thing that we should maybe keep in mind. The fundamental counting principle. When you guys finish writing it, look at that example below and see why I'm saying the numbers are going to get higher. We will use this fundamental counting principle to go ahead and reevaluate the last page and make sure we answer both of those correctly. Fundamental counting principle, as you guys are writing it, we're talking about there being two separate events, two separate things that are taking place, or two separate things that are being chosen. With set, what can I say, places, with set place values. And the idea of the fundamental counting principle is if we're trying to think of the number of ways one thing and another can occur, we can use multiplication in order to help us identify the number of outcomes. So if you guys notice right here, I've highlighted two things. I've highlighted the word and, which is not always explicitly stated. Sometimes it's more implied. And then we have this multiplication symbol. The word and multiplication and probability almost always go together when we're trying to count up how many ways something can occur. So this example down below, how many different pairs of letters from the English alphabet are possible? How many different pairs of letters from the English alphabet are possible? Question. Why am I putting two different blanks? It's event 1 and event 2, and what are you choosing, in a sense, or what could you choose for all the options for the first blank? You could choose 26 different letters, right? How many different pairs of letters from the English alphabet are possible? You could choose 26 different letters to be chosen first. Why am I saying that and, even though and is not in the problem at all? Why is and applicable in this case? We have our first letter, right? And maybe it might be a little bit, might make a little more sense if we do it two different ways. We could label this bottom one a first letter. You're choosing a first letter, right? If you want to think about, you have 26 different options for that first letter. If you were to write all of these out, couldn't you go ahead and write literally your alphabet and say A, B, C, D, E, F, G, right? But you have to add other letters to that. So couldn't you go through and write A with everybody? Wouldn't those be a pair of letters? But problem, couldn't we also do B with everybody? See why I'm saying that this is not a case where we want to write out all the different options? Because I've only gotten like part way through and we're already like, yeah, no, we're not going to write out all the options and count them up. True? But how many letters are you choosing to make a pair, kiddos? You're choosing the first letter and the second letter. Do you see when I'm about to put multiplication? You're choosing the first letter and the second letter. So how many different pairs of letters from the English alphabet are possible? How many letters do you have to choose for the second blank? Did they say anything like the letters can't be repeated? No. So we just say how many pairs? Well, we have 26 options for the first letter, 26 options for the second letter, and guess what the math does? It says, sweet, A can go with A can go with B, A can go with C, A can go with D, etc., 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 and that says, and B can go with A, B can go with B, B can go with C, B can go with D. 26 times 26 adds them all up for us, and what do we end up getting? What is 26 squared? 676. There are 676 different pairs of letters possible when using the English language. Doesn't that one multiplication seem to make a lot more sense than actually writing them all down and adding 676 different pairs? Yeah. Brandon.
What about the pairs that are repeated?
Here's the idea. What do you mean repeated?
So like, with the idea of you're saying like A, or if you match A with each letter, so A, A, B, A, C, and let's say we're going to be fluent in A. With that first column in A, you already had A, B.
Well, think about it this way. You have to ask yourself the question, would BA be a different pair than AB?
Oh.
And whenever you're thinking about letters, we're going to treat them like little baby words. And the question is CAT a different word than TAC? Yeah. So in this case, we say it's a different pair. Now, if we're talking about, like, what letters could you grab out of a Scrabble bag? Would you picking A first and then B be different than you picking B and then A? No. You still have those letters to work with. You know what I mean? You still have the same options. When we're talking about words or license plates or telephone numbers, all of those, we would technically say order is important. Okay, order does not. So let's go back real quick and let's ask ourselves the following question, because that's the exact same question that Luca was asking over here, right? Two distinct integers. How did I explain that 4 worked? I said 1 and 8, 2 and 7, 3 and 6, 5 and 4 gets the exact same result as 8 and 1, 7 and 2, 6 and 3, 4 and 5. And is that statement true? Yes. But question, is a computer grabbing at the exact same time? Is the computer grabbing from like a Scrabble bag of letters, the numbers 1 and 8? Or is it specifically generating in 2 different places? Either the 1 first and then the 8, or the 8 first and then the 1. What's the computer doing when it pops up with numbers on the screen? What do you think it relates to better? A systematic way of doing it. Isn't a computer systematic? So if a computer is systematic, question, how many total ways could a computer pick 2 integers? 1 through 12. How many numbers are there, 1 through 12? 12, right? We could say there are 12 different numbers for the first number, and we could say there are how many different numbers for the second number? 12. Ooh, how many different ways can a computer just pick two integers? 144. In this counting of how many different ways a computer can pick any two numbers, the way that Brandon just brought up, that A and B and A are counted two different ways, or each counted separately, what do we actually have to then include? The other way around. I want to go back and double check myself. And your guys' first gut reaction in the front was correct. I was thinking of a Scrabble bag instead of a computer. A computer picks one number and then it picks the second number. Which means if it picks 1 and 8, that's a different way of picking, or that's a different option than picking 8 and 1. In which case, we would have to go back and say, uh-oh, a computer is picking one number and then another. There are 8 total ways the computer could choose two distinct integers. And guys, if we were in section 9.7, we would say, sweet, 8 out of 144. Those are the chances that that's the probability. But we're not there yet. We're just counting up stuff. We're just counting up the possibilities. So good catch, kids in the front. Let's see if we can apply that to the license plate. In a certain state, each automobile license plate number consists of, now, if I were you guys on these types, I would write down the conditions. Write down license plate numbers, and then say what has to be true. 2 letters, then 4 digits, that makes a number. 2 letters, and then 4 digits. And to avoid confusion, which isn't necessarily how California does it, but to avoid confusion in this state, O and 0 are eliminated as options, I and 1 are eliminated as options. Oh, is that what it actually says though? What's actually eliminated? The confusion is between O and 0 and I and 1, but what do they actually just decide to take out? O and I. The letters O and I are not used. You guys are writing down the important information. I'm just going to write down how many letters are legal to use and how many digits or how many numbers are legal to use. Alright, how many letters are we allowed to use then? 24. 26 letters in the English alphabet. We're not allowed to use O or I. So 26 minus 2 is 24. How many single digits are we allowed to use? And we're going to put 4 of them together, but how many single digits are there in that? 10. 0, 1, 2, 3, 4, 5, 1 through 9, and also 0. So there are 10 possible digits that we're allowed to choose from. Careful. That's how I read it first as well. To avoid confusion, they're just going to say don't use O and don't use I. Good catch, good catch. They just say don't use O, don't use I, so the only O will be 0 and the only, well, they're only using 0 and 1, not O and I. Our case is, to pick a license plate, you can have one letter and another letter, so we can say first letter, second letter. And what else can you put together? Or what else do you need? You guys see how my blanks represent my different filling in of the scenario? So I have the first letter, second letter. So I'm supposed to choose 2 letters. Then I'm going to have my first digit, my second digit, and I'm missing 1 blank, right? My third digit, and my 4th digit. It's a little hard sometimes to think about when they say a 4-digit number. Don't think of all the numbers. You don't have to think about all the numbers from, let's see, where are all the digit numbers? 0 to 9,999. You can think about them with separate digit places. Did they say we're not allowed to repeat? No, we're allowed to repeat. So question, how many letters do we choose for the first letter of the license plate? We're allowed to repeat letters, so how many letters do we still have to choose from? How many numbers are to choose from for the first digit? So it's total number of options. 24 squared times 10 to the power of 4. Possible license plates. Now, is that a huge number? Yes. Did you plug and chug it and get a nice answer? And the answer is yes. Something that Luca was mentioning earlier was in the math and probability menu, there is that snazzy NPR and NCR. What do you guys think of the license plate? Would the license plate be different? Even if they had all the same components, if the order was rearranged, would it be a different license plate or the same? Same components, but if you were to switch the two letters or switch a couple numbers, would it be the same or different? Yeah. Like a telephone number, even if you have all the same numbers as someone else, but the numbers are rearranged, isn't that a different telephone number? So in this one, order is important. There actually is another way of solving this one. We'll go ahead and wait until we talk about permutations and combinations. This is one way, the fundamental counting principle of adding up. Let's see if we can apply this principle to choosing 3-digit numbers with restrictions. 3-digit numbers with restrictions. We've already talked about, if we're talking about the digits separately, like in a number, we can talk about overall, in general, without specific restrictions. We have the digits 0 to 9, which means we have how many total to choose from? 10 possibilities. Now, in every single one of these, they say that we're forming what? A 3-digit number. So we're going to say we're going to choose the first digit and the second digit and the third digit for every single one. This allows us to not have to think about all the different 3-digit numbers, which would be from 0 to 999, and then take away all the ones with 0. That's the way of like adding up all the options. In your brain, you can think of all the numbers 0 to 999 and say take away all the ones where the first digit is 0. What's that? Let's see, 001, 002, 003, all the way up to 099. That's one way to do it. Take away all those ones that start with 0. The other way is to say, oh, cool. You know what? Out of all those 10 possibilities that the first digit can be and the second digit can be, the third digit, which is the leading digit, can't have a 0. It's just another way of thinking about it. The ones digit, there are 10 different options, 0 to 9. The tens digit, 0 to 9, 10 different options. The hundreds digit, oh, they want 1 through 9. They don't want 0. So there are only 9 options. How many numbers are there total? 9. Kind of makes sense. 0 to 99 are illegal. But from 100 to 999 are all able to fit that condition. Letter B. What if the leading digit can't be 0 and no repetition of digits is allowed? Ugh. First digit can't be 0, but isn't it going to be somebody? There are 9 different options, but once one of those numbers is used in the second blank, 0 is allowed. So like, oh, 10 options. But you just used one, so now you only have 9 left over to use. And the last one, 0 is allowed, 10 options, but now you've used 2 numbers already, so now there are only 8 options left.
648.
Letter C says, leading digit can't be 0, there are 9 options. Oh wait, repetition is allowed. So therefore in the second digit, in the tens digit, 0 is allowed. So all 10 of those original digits are allowed to be used. Repetition is okay. But the very, very last digit, it says be a multiple of 5. Wait, hold on. What does the ones digit have to have in order to be a multiple of 5? Either a 0 or a, so how many options can I put in that last one? Just 2. This last one says the number is at least 400. There are 2 different ways of doing it. One way is to say, okay, fine, I can have all the numbers from 400 to 999. That's one way. Let's see if that matches up with, if we were to say at least 400, well, that seems to be no restrictions on the 1s or 10s. But on the hundreds, we're only allowed to have 4 through 9 as an option. So 4, 5, 6, 7, 8, 9. Isn't that 6 different numbers that are possible? Some of you get a little confused by this because you would say 599, but you forgot to count 400. There are 600 different options as to when this will be true. All of this, we've been using something called the fundamental counting principle. And it's not a bad way, but sometimes it might be nice, instead of having to do these separate blanks and thinking about them like that, to maybe, or maybe if there's an alternative, think about something called a permutation. Kiddos, as you can tell, sadly, we're not going to finish 9-6 today, so we're going to have to continue it tomorrow. We're just going to see how much we can get done with today and tomorrow. We might have to even move that test to Monday, which is a bummer. If you remember, the reason was because we were all behind when we came into classes. Permutation and ordering. What do we do when order is important? As it has been with the license plates and with the pairs of letters and even with the computer generating numbers, order has mattered. And ironically, every time that we have written these blanks, the order has mattered as well. Because if you think about all 3 of these, sorry, 1, 2, 3, 4, 5, all 6 of these letters, if we were to arrange these letters, imagine you had 6 Scrabble tiles, we could do this problem using fundamental counting principle and say, hey, how many options could we choose the first letter that we put down on the Scrabble board? But how many letters do we have left? 5. How many do we have left after we choose 2? 4. We could use 6, P, 4. And that's what we're going to develop tomorrow, how one applies to the other. All right, cool kids. I would start section 9-6. You just might not be able to totally finish for tomorrow. So close. I just might ask for stuff I can't